All right, we're moving into section 3.4 on this screencast and keeping on our learning of our rules of differentiation. So in the previous one we talked about the differentiation of a constant, what's the derivative of a power, a variable to a power. Now we're going to evolve into the product and the quotient rule. So we will continue our learning of shortcut techniques on how to find a derivative. We will evolve to learn the product and quotient rule. Please make note that the derivative of two products is not the product of the derivatives, and the derivative of two functions divided by each other is not the quotient of the derivative. So it's just not as easy as taking the derivative of each one of the individual functions and putting that together, okay? So you have to know the rules. So if F, get my marker going, and G are differentiable at X, I'm going to actually move this up a little bit so I can keep that there for when we do our first two products, then the derivative with respect to x of f of x times g of x is denoted by this, where I go f of x times g prime of x plus f prime of x times g of x. And this is actually proved in your book if you would actually like to go to this section and look at that proof. So again, it's not just f prime times g prime. That's not the derivative of that. It is basically taking your original function, or the first one, times the derivative of the second function, then taking the derivative of the second function times the original second function. Okay, so first we want to say that, and another way to say that, and this is the way I normally remember it, is that we take the first times the derivative of the second plus the second times the derivative of the first, okay? And that's how I remember it. Now, can you memorize this formula? Absolutely, but this little saying is one, if you get it in your head, it kind of sticks. So, the product rule is the first times the derivative of the second plus the second times the derivative of the first. So this is what I'm going to refer to as the first, and this one is the second function, or correspondingly f and g. So we could put an f here and a g here. They are being multiplied together, so by the product rule, this derivative, we're going to take, our first function, times the derivative of the second. Now the derivative of that, we're going to take individual pieces, so I bring the 2 out front, decrease that power by 1 to give me a 2x, and this is a constant, so the derivative is 0. Plus, the second function, x squared plus 4, times the derivative of the first. So by the power rule, bring the 3 out front, decrease the power by 1 is 3x squared. And you have a constant back here, which derivative is 0. Therefore, this is basically just taking the first step there. Now, that's the calculus behind it. The rest of it is algebra. So what we have to do is kind of do a backwards distributing here of both of these terms, since the single term is in the back. So I would take 2x times x cubed gives me 2x to the 4th. Negative 8 times a positive 2 is a negative 16x, plus distribute the 3x squared times an x squared gives me a 3x to the 4th, and then a 3 times a 4 gives me a 12 with that x squared. So again, we're just simplifying using algebra. Notice that I end up having some common terms here that I could put together here and here. So that would be a 5x to the 4th. Plus, I'm just going to grab the next one in descending order as a 12x squared minus the 16x. And that right there would be our derivative. Okay? So, take the first times the derivative of the second plus the second times the derivative of the first. All right. So here we're going to let this be f, and we're going to let this in parentheses be g. They are being multiplied together, so we can use a product on this. And so actually you can use a different method, which here and there I'll talk about that later, but we're just going to use the product rule and practice that. So f prime of x represents the derivative of f. So when I have this notation, we want to designate that we are taking the derivative so that we know that they're not just the same thing. All right, so we're going to take the first times the derivative of the second. Now, I'm going to rewrite this. Remember, this is actually a fractional exponent. So I get 2x to the 1/2 plus 1 as that g function. So when I need to do my power rule, I need to multiply this out front. So take 1/2 times 2, which is just a 1. And then I need to decrease this power by 1, which is actually a negative 1/2. So 1/2 minus 2/2 is negative 1/2. So here's my first. the derivative of the second, we bring the 1/2 out front, multiply, we get a 1. I'm not going to write it. And then decrease the power by 1 gives me a negative 1/2. Notice I have a constant, which has a derivative of 0. Plus, I need to now take the second function. Now I'm going to write it with the fractional exponent, because if I have to distribute, then it would be easily done with that fractional exponent. So there's the second, times the derivative of the first, which is just a 2x. Bring the 2 out front, decrease your power by 1, gives me a 2x. Now again, this is the case where we have to do some algebra. This is all the calculus that I need behind that. Now I need to simplify, because you don't want to leave your answer like this. So first I have two bases that are the same, and when the law of exponent tells me I have to add those two things, well, I have 4 halves here, if I get a common denominator, minus 1/2 gives me a 3 halves. Plus, when I now have to distribute here, kind of backwards in a sense, I need to take 2 times 2 gives me a 4, and x to the 1/2 times x to the first. Now remember, I got to add those exponents. So 1/2 plus 2 halves for the 1 gives me 3 halves, so I have x to the 3 halves. Then I have to take 2x times this one, which just gives me a 2x. Now notice I do have common terms here, so I can actually put this and this together. Therefore, my final answer would be 5x to the 3 halves plus 2x. And that is perfectly okay to leave as the derivative. Don't worry about simplifying that into radicals. When we get to this point in calculus or in higher math, then we are working with fractional exponents versus a radical. Okay, so that's the product rule. Again, the derivative of two products is not the product of two derivatives, okay? So you cannot just take the derivative of one and multiply it by the derivative of the next, okay? Now we turn to the quotient rule. Well, the quotient is an answer to a division problem. So that means that I have a division or a rational function that I need to take the derivative. So we're going to let f and g be differentiable functions at x, and g of x is not equal to 0, because where is g of x? I'm going to let the function h of x be f of x over g of x, and that would be a problem if that function is 0, because I can't divide by 0. Therefore, here is the rule. H prime of x is equal to g of x times f prime of x minus f of x times g prime of x all over g of x squared. Okay? Now, I'll be honest, as I'm writing that, I am looking at my paper because this is by definition with f and g what it is, but this is not the way that I remember it in order to keep it right in my head. So I'm going to show you kind of what my AP Calculus teacher taught me, and this is just the way that I've practiced doing a quotient rule, and that's the way it's just stuck with me. So you can use either one. Again, you can memorize this formula, but you do not have to. Notice this time makes a difference because I have a minus as to which one comes first. The previous one didn't matter. As long as you got both of those when you add, it doesn't matter which order. All right, so I'm going to treat this as a fraction and call it the fraction of high over ho. Okay, I don't know, think of the 7 to worse at that point if you want. But, because they had a song that went with that. But here is the way that I was taught how to do that. So the derivative of this fraction of high over ho, it's just kind of a thing that you just remember, okay, is you do ho d high minus high d ho all over ho ho. Okay? Now, there's other versions to this. They have high over low. Some people say it's more politically correct, but we're going to do it this way. If you want to change this to low instead of a ho, then you can do that, okay? So, ho d high minus high d ho over ho ho. And that's the way I do it to this day, to remember it. And making sure that you remember this order, that the ho is in the bottom and the high is in the top. So, ho d high minus high d ho over ho ho. The d there stands for the derivative. I have to take the derivative of that all over the original function that's in the denominator squared, okay? So, we're going to do this. We're going to treat this one like high and this one as the ho. And we are going to take the derivative using the quotient rule of this x squared plus 3x plus 4 all over x squared minus 1. So that derivative, we're going to do ho, which is x squared minus 1, d high, so I take the derivative of this, which power rule, bring the 2 out front, decrease it by 1, gives me a 2x. The derivative of any linear term is just the constant out front, and the derivative of a constant is 0. So the derivative of that top function is 2x plus 3. Minus high, which is x squared plus 3x plus 4, d ho. So that means I got to take the derivative of the denominator, which is just a 2x because the negative 1 goes to 0. All over ho ho. So that means I need to take this function and square it. So I get x squared minus 1 squared. Okay? All right, so now let's simplify the top. Again, that's where calculus is finished. We're now going to just simplify using algebra. Now notice this is a binomial times a binomial, so I have to FOIL. So I'm going to do first, which gives me 2x cubed. Outside gives me a plus 3x. Inside is a plus 3x squared minus a 2x for the outside and inside. And the last term there, minus 1 times a positive 3 is a minus 3. Then I have a negative here and a 2x that I have to distribute through each. So be careful. Don't forget about that negative. So 2x times x squared is a 2x cubed, but I have a minus of that. So a minus 2x cubed, then a 2x times a 3x is a 6x squared with a minus is a minus 6x squared. And then we have a plus 8x, but with a minus becomes a minus 8x all over the x squared minus 1 to the 4th power. Okay? All right, so on the top, notice that the 2x cubes are gone. That's very nice. Because then I could practice putting together this x squared and that x squared as a minus 3x squared. And then I have a minus 2x and a minus 8x gives me a minus 10x. Then I have a minus 3 as my only constant, all over the x squared minus 1 quantity squared. Now, this is an okay answer for me, so if we're on a test or something like that, you were definitely able to just circle that and leave that. But if you notice in the top, they all have negatives. So your book and my math or my lab math may end up factoring out a negative, and you have to realize that those answers are the same. Now, in a multiple choice situation, so if I take a negative, that means I change all the signs in the top, but I just treat it as kind of the negative on the outside of that fraction. Now, hopefully in a case where you have to type in the the derivative of that function, then hopefully, sorry, I'm trying to get that update thing out of the way. Hopefully, what you give will be something equivalent to what they would test with. Okay, and assess. So, all right, so let's move on. Let's move on now to the back side here. Get rid of that, sorry. Okay, so now we're going to look at another one that we have to do using the quotient, but also we're going to add to that we now have to find the equation of the tangent line. So remember, the derivative of a function is the slope of the tangent line, so to write the equation of that line, we would have to know what that slope is, okay? All right, so notice here that I end up having this piece here, and it is a function. Notice I have a degree of -1 though, okay? So when I have a -1 power, recall that that makes that expression, in this case, move to the bottom and make it a +1 power, but I'm not going to write it as a +1, okay? So this is what my function is. In order to write the equation, remember, I need a point. I need 3 comma something, and how do I find that something? Well, here is the y value in disguise for that function, so that means I'm going to have to plug 3 in there to figure out what f of 3 is, and that will give me my y value. So let's go 3 squared plus 1. All over 3 squared minus 4. Well, 3 squared plus 1 is 10. All over, this is a 9 minus 4, which is a 5. Therefore, I get a point now of 3, 2. That's the point I'm going to use for my equation. But I still need the slope of my tangent line. So that slope of that tangent line is going to come from finding the derivative of that function. So this is a quotient, so we're going to end up doing our little ho-de-hi, or you can do the formula. Doesn't matter to me. I'm going to do ho, which is x squared minus 4, d-hi. Derivative of the top is just a 2x, minus hi, d-ho, again, I get a derivative of 2x, all over that denominator squared. So, now is the point that I can do some algebra. Yes, could you put in x equaling 3 at this point? Yes, but it would be tedious. You might make a few mistakes. So let's just go ahead and simplify in terms of x. By distributing kind of backwards here, we get a 2x cubed minus an 8x. Here we have again a negative. Be very careful. We got to distribute that and the negative. So I get a minus 2x cubed minus a 2x all over x squared minus 4 quantity squared. Now, fortunately again, these two are gone. That's very nice. I'm left with negative 8 minus 2x, which is a negative 10x, all over the x squared minus 4 quantity squared. So that's as far as we could go. If you were asked to find the derivative of that, that would be my expectation. But here we have to go one step further and find what is that derivative when x equals 3. So I'm going to plug 3 in. Gives me negative 10 times 3. All over, we get 3 squared minus 4. That's a squared. That I have to then square. So I get negative 30. All over, 9 minus 4 is a 5. Squared is a 25. And when I reduce that, it looks like negative 6/5 is going to be my slope. So between this and this point up here, we are actually going to be now writing the equation of our tangent line, okay? So this is something that you need to master. So we need to go y minus the y value that we found over here, which is 2, equals negative 6/5 times x minus 3. And from here, we get to distribute negative 6/5 and then solve for y. So I get y minus 2 equals negative 6/5 x, and negative times a negative becomes a positive, and unfortunately, 6/5 times 3, nothing will cancel. So that ends up with an 18/5. That when I add 2 to that, well, the equivalent would be 10/5 when I get a common denominator. So my final answer would be negative 6/5 x plus a 28/5. Now, if you're unsure on those fractions, please make sure you make use of your scientific calculator so that you can do that. Okay? All right, very good. I apologize for this little window that's open up here. I'm not sure what's going on. All right, so we'll just scroll past that. And now we are given some problems here to find the derivative of, but it may be in disguise somewhat. So like these all look like quotients and possibly like a product over here on this one. But we can simplify a function first and then make life a little bit easier. Now, this is a reminder here of our power rule. Remember, if I have f of x equals x to the n power, then f prime of x is equal to n times x to the n minus 1. So remember, we can bring the number out front, decrease that power by 1. So yes, you can definitely use the quotient rule on this, but if you remember that these variable in the bottom with a power can be brought up top using the negative exponent, then it's so much easier to be able to use negative exponents versus doing a quotient rule. So make sure that you do that. Simplify your functions a little bit first and then take a derivative. So like this derivative, all I'm going to do is bring that negative 4 out front and multiply it by 6 to give me negative 24. Now remember, decrease this power gives you a negative 5, not a negative 3. You're subtracting 1, so negative 4 minus 1 is a negative 5. So this would be an okay answer, but if it's a multiple choice situation, you may have to realize that it is also equivalent to negative 24 all over x to the 5th, where they would bring that variable back down to the bottom. Okay? Notice with this, yes, you can do a quotient if you want, but you don't have to, because if you recall, whenever I have a fraction like this, if I distribute that denominator to each of the terms in the numerator, you can end up rewriting that function without a fraction. So if I do that, remember this is 3w to the 16th all over w to the 6th minus 4 over w to the 6th. Now, granted here there's nothing you can simplify, but I could cancel here and leave me with 3w to the 10th minus, now I'm going to bring this up top and make it a negative. Okay, so that gives me a new look at the same function, to which the power rule is going to be so much easier to do here than a quotient. So here's my derivative. Remember, don't be lazy. Make sure you write your notation. Bring your number out front, multiply by 3 gives me 30, decrease by 1 gives me w to the n, or w to the 9th, excuse me, minus, now, negative 6 times 4 is a negative 24, and you have a minus out here, so that actually becomes a positive 24. Decrease by 1, minus 1 gives me a minus 7 there. And again, this would be an okay answer. If you were typing, it should be equivalent, unless they specify no negative exponents. But you could also write that, rewrite this one, because that doesn't change. But I could write this as 24 over w to the 7th, and that also could be a valid answer for that derivative. Okay? All right, very good. Let's move forth. This one is a practice with some fractional exponents. So if it's a radical, we don't do radicals with calculus. We do them as fractional exponents. So I'm going to write this as 6z to the 1/3. Rewrite that function a little bit. Because now I can take the derivative of that by bringing the 1/3 out front. And then, or you could do it this way, rewrite it separately. I would go ahead and multiply the 1/3 by 6. But if you're not used to that, 1/3 out front of this guy, keeping the 6, don't putting them together just yet. Z, now decrease that by 1. 1/3 minus 1, well that's the same as 3 over 3. So that gives me a negative 2/3 as that. Now, go ahead and multiply. 1/3 of 6, or divide by 3 is 2. Z to the minus 2/3. So that would be an okay derivative for me. But in essence, if I say no negative exponents, then 2 over z to the 2/3 would be a final answer as well. If they prefer to leave it in radical form, then 2 over, remember, power over root, so I'd have the cube root of z squared as a third possible answer for that same derivative. So make sure in a situation that you watch the directions as well as kind of check the answers if you're in a MyLab sense, MyLab math sense. Okay? All right. Now this one, unfortunately, there's nothing you can reduce. You can't divide this into these down here. Only the bottom can you divide like we did up top. So this is actually just a quotient rule. Okay? So, but the quotient will involve this fractional exponent. So that's why I wanted to show you this one as well. So for a quotient, we're going to do whole, 2x squared plus 4. D high. Now, taking the derivative of this, you got to take 3 times 5 halves over 1, multiply straight across, gives me a 15 halves. But then I decrease that 5 halves by 1. So 5 halves minus 1, well, 1 is the same as 2 out of 2. So I get a new fraction of 3 halves. So if you're unsure and shaky on fractions, make sure, again, I'm strongly emphasizing you use that scientific calculator so you don't make any mistakes. Minus high d ho. So I need 3x to the 5 halves times the derivative of the bottom. Now, that's going to go to 0, so I just need this one, which is going to be a 4 and an x. All over that denominator squared. Now, notice in that denominator, we actually have a common 2. So I could take a 2 out of here if I wanted to, and I have to do it twice. So that means I take a 2 from one and a 2 from another. So actually, I could take a 4 out of the bottom. So let's do that. I would take out a 4 and be left with this x squared. When I take a 2 away, that gives me a 2 quantity squared. So I can rewrite the bottom like that if I wanted to. All right, let's distribute the top. So this times this, and this times this. Now, let's do 2 times 15 halves. Again, the 2's are going to cancel. If you're shaky on your fractions, make sure you use your scientific. And I have x to the 3 halves times x squared. So that means I have to add those exponents. So 2 plus 3 halves, this gives me a 4 over 2 as a common denominator. So that 4 halves plus 3 halves gives me a 7 halves as my fraction. plus, now this one's not too bad, I just have to do 4 times 15. So 2 goes into 4 twice. 2 times 15 gives me a 30. X to the 3 halves. Don't have to combine letters here. Minus, I'm going to multiply numbers together to give me 12. And then I have to do 5 halves plus 1. Well, that's 2 halves plus 5 halves is another 7 halves. And so what I have is 2 terms here that I can combine together as this 7 halves, and that x to the 7 halves gives me 3x to the 7 halves plus 30x to the 3 halves all over 4 times x squared plus 2 quantity squared. So again, this would be an okay answer for me if I had that given to you on a test situation, unless I ask you to fully factor that. And in that case, the top is not fully factored. Okay, so I would be able to factor out a common 3. And there's an x in common, and when we have x's in common, we take the lowest power. So I would take out an x to the 3 halves. Now, what would I be left over? Well, take the 3, I need an x. So what power of x do I have here that when I add it to 3 halves gives me 7 halves? Well, if I take 3 halves away from that, I get 4 halves, which is 2. That's the power that I have. And then what do I need here? I just need a 10 left over because I took all of this and I took the 3 away. So I have a plus 10 all over that 4 times x squared plus 2 quantity squared. Okay. All right, very good. So that is our derivative there for that quotient function. Okay. All right, moving right along. Now we're getting into an application here. Remember that the derivative has multiple uses and interpretations. The following example illustrates the derivative as a rate of change of population. Specifically, the derivative tells us when the population is growing most rapidly and how the population behaves in the long run. So we need to find the instantaneous growth rate of the population. Instantaneous. Hopefully you reminded that that is the derivative of our function. So for part A, I'm looking for p prime of t of this quotient. So I'm going to take ho d high, which is 300, minus high d ho, which is just a 1, all over the derivative, or excuse me, the denominator squared. Okay, so ho d high, that's a linear, so I'm just left with 300, minus high d ho, here's a linear, I just left with the 1 in front, that guy is a 0. So when I simplify by distributing here, I get 300t minus plus 900 minus 300t all over our t plus 3 quantity squared. Now, these cancel, and I'm just left with my final answer of 900 all over t plus 3 quantity squared. Okay? All right. So that's part A. Part B then is asking us what's the instantaneous growth rate at t equaling 5? Well, when I have the instantaneous growth rate, p prime of t, I get to now just plug in 5. So I want p prime of 5, which is 900 all over 5 plus 3 quantity squared. So I get 900 all over 64, which is a decimal of 14.0625. And that's the growth rate, basically, that we have for the population behaving and growing, okay, per year or per week or whatever it is, whatever the time unit is here, okay? Now, part C, you can read on your paper there, it says estimate the time when the instantaneous growth rate is at its greatest. So this is kind of harder to answer at this point. We will figure this out but later mathematically, but at this point you don't know exactly how to do it. They want you to logically remind yourself that this is my growth rate, and in order for this to be the highest, since it is a fraction, then that means that this has to be the smallest. So anytime that this grows, that makes my ultimate number go smaller. So if I can find out when t plus 3 quantity squared is the smallest, then I would be able to determine the maximum value there. Now, if I were to say, okay, when is that the smallest? Notice that also we have a restriction here of t greater than or equal to 0 because we're working with time. Well, if I let that be 0, then anything bigger than 0 is going to be bigger than that. So if I'm looking for the smallest, that has to be at when t equals 0. That's the smallest that will ever equal whenever we have that there. Okay? All right, I'm going to scroll back up here and do D over here. We want to then evaluate and interpret the limit as x goes to infinity of our p of t. So that's 300t all over t plus 3. Now this is a limit at infinity, which warrants our horizontal asymptotes. So remember, we have to, as we go to infinity, take the highest power in the denominator and divide that. So what I now get is the limit as x goes to infinity of 300 all over a 1 plus 3 over t. 300 all over 1 plus 3 over t. And as I go to infinity and I get larger and larger and larger, this fraction goes to 0. That's from what we had in our earlier sections in chapter 2. So therefore I get 300 over 1, which is 300. Now remember, this is the rate of growth, okay? Or I'm sorry. I'm not on an instantaneous rate of growth. I'm on the original function, which represents population. So this basically means that our population approaches the value that I get out of my limit, which is 300, as time gets large. So as time goes to infinity, and actually I should not use x there, I should use t there. So I should probably modify my notes. Okay, so this should be a t, and that should be a t, and that should be a t. Okay? All right, now for part E, what you need to do is it says use a graphing utility to graph the population and its growth rate. So I will tell you, I use Desmos, and so you have to kind of widen out the view a little bit to see what the graph looks like. So here, I'm going to come up and do something like this. Our original function is approaching 300 as we go to infinity, so 300 would be about here. This is our P of t. And then if I were to graph the rate, which is this guy right here, then what it does, it's actually a decreasing function. It ends up kind of decreasing and going in this direction. So this is P prime of t. So you can actually practice that. Under Desmos, again, you would put in your derivative, and you would also put in the original function as well to get that graph. Okay? All right, very good. Let's keep it moving. Now we're going to find the first and second derivative and then also find an equation of a tangent line down here. So first and second derivative, I need to use a product rule on this first one because I have two things that are multiplied together. Call that F, call that G. And if you recall the kind of mnemonic device, we take the first times the derivative of the second. Well, that's a constant, so that's 0. Bring the negative 4 out with that negative, gives me a positive 4. And decrease the power by 1 is next to the fifth, negative fifth, plus the second times the derivative of the first. So I'm going to take a derivative of that as a 3x squared. Now remember, this is a product, so we don't have a denominator here. So we're going to set that equal to, multiply this together, we get 4x2 to add the exponents, negative 2. This has a minus here, so I have to do a little distributing, but there's a plus, so I don't have to worry about changing too many signs. So 3 times 4 is 12, x squared, that one's the easier of the two, minus, no number to go with 3, so we'll rewrite 3, x to the minus 4 times x squared. Add those exponents again, gives me a negative 2. Now notice I can put these two things together and give me x to the minus 2 plus 12x squared. And that right there is our first derivative. So that's f prime. Now from here, to take the second derivative, now I just need to take the derivative of this. So I'm going to bring the 2 out front, decrease the power by 1, gives me a negative 3. Bring the power out front, multiply by 12, gives me a 24. Decrease the power by 1, gives me just an x. And so therefore, there's our first and our second derivative of that function. Okay. All right, very good. And then the last one is writing the equation of a tangent line again, but it's got a little twist to it in the way form of a function. So if I need to write the equation of the tangent line, first off, I need a y value. Because the x value is 3, well, what's the y? That means I got to plug that into here. So what is g of 3? Well, it's f of 3 all over 3 minus 1. Well, what is f of 3? They gave it to us in the original problem. They said it's a 2. And 3 minus 1 in the bottom is a 2. Therefore, my y value that goes with that x equaling 3 is a 1. Now, that's what I need to write the equation, but I also need the slope, which is going to be the derivative of that function. So this is a quotient rule, so I'm going to have to do a little bit of that ho d high stuff. So I'm going to take ho d high, and I'm just going to write it as f prime of x, minus high, which is f of x, d ho, well, that derivative of the bottom is a 1, all over that denominator squared. Now, normally we would go and distribute and simplify things up, but here, notice that would kind of get a little crazy. So I'm going to go ahead and find what is g of 3. And I'm just going to plug in those numbers. So sometimes it's okay to do that. Other times it'll be warranted to go ahead and simplify. So everywhere I see an x, I'm going to put a 3. So I get 3 minus 1 on the top, which is 2, times the derivative of f at 3, which they gave it to me. That is 5. So I'm going to do 2 times 5 minus the function value at 3 was given to be 2, all over 2 squared. So 2 times 5 is 10, minus 2 is an 8, all over 2 squared, which is a 4. Therefore, that's equal to 2. And then the equation of my tangent line comes right along from that, because that piece right there is m. I also have my point over here that I can write the equation of my tangent line. And so now using point slope, I can go y minus the y value equals the slope times x minus the x value, which is 3. And when I distribute my 2, I get 2x minus 6. And when I add over the 1, the final answer would be 2x minus 5 as the final answer there. Okay, so that is the end of section 3.4. We will actually move into the next section, which is doing some more derivatives of trig functions this time, and we will get more tools within our toolbox. Until next time.